In this video, we'll take a look at the ANOVA approach to the general linear model. We can write the sums of squares for this general linear model in terms of matrices. Again, just to remember that this stands for the total sum of squares, and this stands for the error sum of squares, or residual sum of squares, and this is our regression sum of squares, or model sum of squares. Okay, so our total sum of squares, remember this is going it's exactly our variance in the y values without using any of the other predictor variables. And how do you get that? Well, how do you compute the variance? Maybe you want to think about that and see that in fact this is how you would get the sample variance for just the y values, except for despite maybe dividing by some number of degrees of freedom. Here's our error sum of squares, okay, and all it is it's just the square of all the errors, okay, and then summed up, okay, sum of squared errors. So that's exactly what you get when you do the transpose of E times E itself. Okay, it's just the dot product of the E vectors there, and E is, you know, our y minus the y hats, right? And so this is y hat, you know, x, our data matrix, times b, that gives you our y hats. So y minus y hat is an E transpose there. And then I got the same thing over here. Okay, so you want to, as an exercise, you'll want to multiply through here and make sure that you actually do in fact get this, where H is your hat matrix. Oh, by the way, I probably neglected to say that this J matrix, remember, is a matrix of all ones. Okay, but do see that when you carry out this matrix multiplication that you in fact get this product over here. You might try taking the transpose of this stuff first. You could try that. The transpose of the difference is the difference in the transposes, and go from there. Maybe you get a y transpose times y. Hey, it's showing there. It's showing up over here when you take it in with the identity. So try that out. Finally, our our regression sum of squares. Big mistake there. Sorry. Regression sum of squares is given by B transpose x transpose y minus 1 over n times y transpose times another J matrix full of ones times y. And it would be a good exercise for you to go through and actually check that this indeed gives you this regression sum of squares. Okay, so it turns out that these forms are very special. These are called quadratic forms. A quadratic form is a matrix product that looks like this, where you have some matrix, and then on either side you have a matrix. You're multiplying on both sides by the same matrix, but on one side it's transposed. So you can look through here, you can see in fact all of these are quadratic forms. In the middle here you've got the identity minus 1 over n times a matrix of ones, and then flanked on both sides by this y matrix, or y vector in this case. Okay. Similarly here you've got y's on either side of I minus the hat matrix, and over here you've got y's on either side of the hat matrix minus 1 over n times the J matrix. This is just a fancy way of getting a bunch of 1 over n's in a matrix, right? That's how you do this, is what that is. Okay, so of course, and this is where A is symmetric, and it's called the matrix of the quadratic form. Okay, so note that these again, like we said, these are all our sums of squares here are all quadratic forms, and the usual variance estimates, our usual variance estimates, MSR and MSE, then are those sums of squares divided by their respective degrees of freedom. And as with linear regression, MSE is an unbiased estimator for the common error variance. So we can use that. It's a good estimator for that sigma squared. Turns out, however, that if I look at the expected value of MSR, it's sigma squared plus some other stuff, which is positive, and all that other stuff is a you can find this in your textbook, but it's a sum of a bunch of terms with all these betas in there as factors. And so if all those betas are 0, then all that other stuff goes away, and then in fact this mean is is exactly sigma squared, and so then MSR is an unbiased estimator. So this sort of provides maybe a sort of conceptual understanding maybe of a way that we can run an f-test for testing to see if the betas are all the same. So under the null hypothesis, you see all of our model parameters are, say, equal to 0. And then maybe the alternative hypothesis is that not all of these are equal to 0. At least one or more of them perhaps are non-zero. And so what you can do then is take a look at this test statistic. Remember, if the null hypothesis is in fact true, then the expected value of the numerator is equal to sigma squared, and the expected value of the denominator is equal to sigma squared. And so maybe sort of these this number divided by this number in your test statistic should be approximately 1, because they should be approximately the same. And so so in this case, you would reject H naught in favor of the alternative hypothesis, provided your test statistic here is large enough. Okay, if it's greater than some f value. It turns out this thing has an f distribution if these things are all equal to 0. So in example 43 here, it says do an f-test for the significance of the regression parameters for that commercial properties model. Hey, it turns out, you know what, we already did this. Just take a look at the tail end of the previous example. Well, by tail end, I guess I mean take a look at the summary of your linear model out. Okay, and here's your f statistic on 4 numerator and 76 denominator degrees of freedom. Okay, you've got 4 numerator degrees of freedom because you have 1, 2, 3, 4 of those betas. I think that's right. And then you've got 76. Right. 4 for your model, and then 76 for your error sum of squares, degrees of freedom. Your p-value is very, very small, so quite likely some of these, at least one of these betas is not equal to 0, quite likely. And if I look at these individual tests up here, these individual t-tests, you can look at these p-values. It looks like 4 of these values are pretty significant. That is, there is significant statistical evidence to indicate that these coefficients are in reality not 0. They could be really, really super small, but that's neither here nor there. There's significant evidence, it looks like, to suggest that the intercept beta naught and the beta 1 and the beta 2, right, and the last one down here, that those guys are significant. And so this guy here, I forget what the variable was, but it's VR. This variable here for VR is probably, we could leave it out of the model probably.